Good morning, good afternoon, and good evening to everyone joining us from around the world. Welcome to VTS Young Professional webinar. We are delighted to have you with us today for an engaging and insightful session. I'm Chedlia bin Naila, Secretary of the VTS Young Professional Committee and Coordinator for the Young Professional webinar series. Today, we are pleased to host Dr. Hossien Eldeeb, Assistant Professor at the United Arab Emirates University. Dr. Eldeeb earned his PhD in Electrical and Electronics Engineering in 2021 and previously had several research roles at the University of Cambridge and Khalifa University. His work focused on wireless and optical communication, cybersecurity, cybersecurity intelligence services, AI, ML for networks. He has published over 60 papers with 1,200 plus actually citations and received multiple best paper awards. Dr. Eldeeb is also very active in IEEE community, serving in leadership roles and contributing to major conferences. We are delighted to explore his perspective on Li-Fi enabled V2X, realistic channel modeling and innovation for next generation connectivity. Without further delay, please join me in warmly welcoming Dr. Eldeeb. So Dr. Eldeeb, the floor is all yours.
Okay, hello everyone. It's a great pleasure to meet you all in this IEEE VTS seminar series webinar supported by IEEE Young Professionals. First, I would like to sincerely thank Dr. Chedlia for the kind invitation and for organizing this event. So, as Dr. Chedlia mentioned, my name is Hossien Eldeeb and I am Assistant Professor at the College of Information Technology at UAE University. And today I will be presenting a talk titled Li-Fi Enabled V2X Realistic Channel Modeling and Innovation for Next Generation Connectivity.
Sorry for interrupting. I'm afraid we don't see your screen, Dr. Eldeeb. So if you can.
Oh, really? Okay.
If you can kindly share your screen.
Okay. This should be already shared. Oh, okay. What about now?
Yeah, now, yes, we do. Yes, we do. So the floor is all yours.
Thanks a lot. So, as I mentioned, today I will be presenting in the topic of Li-Fi enabling V2X communications, channel modeling and innovation for next generation connectivity. So let me take you through the structure of this talk. I will start with an introduction to V2X communication and the Li-Fi technology. Then I will discuss the channel modeling concept and the methodology we use. After that, I will present our work in intervehicular and infrastructure-to-vehicle communication channel modeling. Finally, I will highlight a few key challenges, recent innovation, and the future research direction. So, vehicular communications has become the key enabling technology for intelligent transportation systems. As V2X or vehicle communications can allow vehicles to communicate with each other as well as with the surrounding environment. As we can see here, we can see different forms of vehicle-to-vehicle communication, vehicle-to-infrastructure, infrastructure-to-vehicle, which we commonly refer to as vehicle-to-everything communications. So in a simple word, we can say let the vehicle message while driving, not we. Vehicular communications can add a lot to road safety, the traffic flow, and the passenger comfort as well. So for example, here, in vehicular safety, vehicle communication can allow for vehicle collision warning and the traffic condition warning signals. And in protection for disabled person and children. For instance, the vehicle in behind the school bus can receive a yellow bus warning so that it can give attention to the children who can cross the road. Also, in emergency situation, as well as in cooperative traffic management, where vehicles can share their locations with the traffic management system. There is already several applications for vehicle or for vehicular communications. Most of research efforts, however, focus in V2X based on radio frequency. And the idea of radio frequency is that using the electromagnetic or the radio frequency in the electromagnetic spectrum. For instance, we can notice that Toyota and GM have already equipped their vehicles modules with IEEE 802.11b, which namely dedicated short-range communication system. And also we can see that some growing number of automakers, including Ford, Geely, BMW, Audi, Tesla, and Land Rover, has already started several demonstration and field trials for cellular V2X systems. The problem is the allocated RF band is limited, and then with high traffic scenarios or with high density traffic scenarios, such allocated RF bands will face interference and will result in channel cognition as well as longer delays. So if we think about a scenario like this, which is actually available or already existing in many cities along the world, we can notice how RF can fail to actually provide the sufficient reliability or sufficient quality for V2X communications. And to address this challenge, Li-Fi based V2X communication has been proposed as a complementary or alternative solution in some scenarios. So what is Li-Fi? Li-Fi uses visible light spectrum instead of radio frequency. And the spectrum that Li-Fi use can range or can span the wavelengths from 380 nanometer to 780 nanometer, which can be translated to a frequency from 400 to 800 terahertz. Here we refer to this visible light spectrum. Okay, and the Li-Fi or visible light communication technology is based on the principle of using and modulating the light emitting diode or LEDs in order to achieve both illumination and data communication together, which also will add to the energy efficiency. And here in this slide, I will show you how Li-Fi works in a basic, maybe in basic steps. So if you can here look to this diagram, we have the Li-Fi system or consists of two main hardware components, the transmitter side and the receiver side. Transmitter here is represented by LED and the receiver will be represented by a photodiode, right? So now the LED switched on and off at very high speed. When the LED is on, it represents a binary 1. And when it is off, it represents binary 0. So if we use a controller to encode the data into the right signal by controlling this switching, we can then utilize these features and transmit our data through the intensity variation of the LED. And this variation or this light propagation will travel through an optical wireless channel until reaching to the photodetector or to the receiver. It is important to know that during propagation, the signal may experience attenuation, reflections, and interference as well. So as the receiver, the photodiode, it detects the light intensity variation and converts them into electrical signal, which can be then processed and decoded in order to recover the original signal. Before moving forward, I wanted to summarize some key contribution timelines. And here I divided this key contribution to three main phases. The first one is a foundation phase, in which I would like to give light or to shed light into the first invention by Alexander Graham Bell, which is a photophone in 1880. And this followed by several experimental demonstration of infrared-based indoor communications by Jelfer and Babset. Okay, next, and specifically in 1999, we noticed a significant research efforts from Professor Nakagawa team and Keio University in Japan for utilizing LEDs for communications and achieving a megahertz range experimental system. This has motivated IEEE to initiate the first standard for visible light communication or Wi-Fi, which named as IEEE 802.15.7. And in the second phase, from our key contribution or key contributors, I wanted to highlight the coining Wi-Fi concept by Professor Harald has, which opens the door for high-speed bidirectional optic and wireless communication networks. This, of course, followed by several research efforts, specifically utilizing OFDM techniques, which also allow for extremely high-speed visible light communication systems. The first commercial Li-Fi has been appeared in 2015 by Pure Li-Fi, and again this has motivated IEEE to enhance the existing standard, as well as including high-speed MIMO and the mobility support. Mobility support here also initiate for the appearance of utilization of vehicular visible light communications, which is the third phase which I would like to highlight. For example, between 2015 and 2019, we noticed some proof of concept using headlights and tail lights by several research groups, including Professor Murat Group, Afghani Group, and the Qadri as well. This also followed by several advancements in V2V and the V2I channel modeling and hybrid radio frequency and the VLC system and etc. research efforts. So what is the advantage of Li-Fi system that provided or that motivated for such extensive research interest? In fact, Li-Fi can offer several advantages, including that it can provide extremely high data rates. Second, it can offer enhanced security. And here I'm talking about indoor scenarios. And this is the reason for that light cannot penetrate walls. Third, Li-Fi is safe and doesn't cause electromagnetic interference. Also, Li-Fi provides a very large available bandwidth. Okay, and at the end, I would like to mention the energy efficient, especially when we utilize the existing LED infrastructure for both illumination and data communication as well. Just to put Li-Fi and Wi-Fi together in one-to-one comparison, we can see several differences between them, but we can conclude that Li-Fi is particularly suitable for high-speed, short-range, and secure communication scenarios. Here we can see several application scenarios, including indoor, in airplane, in meeting room or convention centers, underwater communications, and the most importantly for our talk today, in vehicular Li-Fi communication system. And the main motivation for utilizing the Li-Fi in vehicular communication is the widespread adoption of LED-based lighting. As you can notice here, most vehicles already have LED-based headlights and tail lights, same for street lights and traffic light signals. This makes Li-Fi a natural candidate for V2X communication. However, this research area is still relatively new, and it requires several efforts in different aspects, including the system and the channel modeling, physical layer design, network layer protocols, and etc. One of the important topic is channel modeling, which is our focus for our today talk. So for those who are not much familiar with wireless communications, I would like to define the channel as the medium which we use to transmit information from one point to another one. So from a transmitter to the receiver, where we have a medium in between where the signal propagates through. This is the channel. And we need to highlight here that some phenomena that can happen to the signal during or through this channel, including reflection, diffraction, scattering, and attenuations. Okay. In addition to that here, for example, I'm just trying to differentiate between those kind of characteristic. For example, this is a line of sight connections between the transmitter and the receiver. And here we can notice the reflected path from the transmitter to the receiver. Same for diffracted path, and the scattered one. In addition to those, I would like to mention that when modeling V2X Li-Fi channels, it is important to consider the practical parameters for the transmitter, receiver, and the channel. So for transmitter, we need to consider the radiation profile, transmit power, spectral profile, and for the receiver, responsivity, receiver diameters, and the field of view angle can also impact the received signal. Same for channel where we need to include weather attenuation and road reflectance conditions. Okay. One important point I want to focus on it right now is the radiation profile. As you know, in most work done in Wi-Fi or visible light communications, the commonly used model is the Lambertian model, which we can see here in this photo. Such ideal Lambertian model can work well for indoor luminaries. However, and by the way, this can be represented by this well-known formula or well-known Lambert formula. But the question is, does this work for B2X light sources? So the questions can appear in the next slide here. When we look to the radiation profiles for outdoor environment, from commercial headlights, tail lights, or street lights, traffic lights, and the tail lights as well, we can notice the huge difference between those street light pattern or headlight pattern and the ideal Lambert radiation profile, right? So if you agree with me on that, so this one reason that can highlight the need for realistic channel models that can take into account such asymmetrical radiation pattern. Together with the asymmetrical radiation pattern, weather condition, sunlight, road reflections, all of these highlight or motivate the need for realistic channel model, right? And here I would like just to skip such a slide, but here I would like to say that in our study, we wanted to consider all these effects, and we found this very interesting methodology to consider for channel modeling in Li-Fi V2X communication, which is based on ray tracing of optical studio software. So the advantage of this ray tracing channel modeling include the ability to integrate any realistic light source radiation pattern, whether symmetric or asymmetric. Also, the option of using typical CAD models of real objects, and as well as the wavelength-dependent reflectance for the wood and the material, including the different reflection types like specular, diffuse, or mixed, can be also integrated. This ray tracing methodology can also allow for high number of reflections for better accuracy. The definition of weather condition is also applicable in this software. Okay, so how we can utilize this software to model Wi-Fi communication channel that can be described here in this slide. I rename this methodology with a three-step methodology because it consists of three main steps. The first one is design, in which we design the 3D simulation platform or the 3D simulation model of our test environment. Then we integrate the typical CAD model or design them inside the software. For example, in indoor, we can include tables, human being, and for outdoor scenarios, we can integrate details, building, roads, and etc. So this is the first step of the software. The second step of this replacing methodology is called the define, in which we define the specification of the 3D environment. Also, we define the parameters related to the transmitter, the receiver, as well as the weather conditions, as we can see here in this slide. Once all definition has been completed, we can move to the third step, which is analyze. Simply, we conduct the ray tracing or the non-sequential ray tracing analysis with Optical Studio, which at the end provide us with an output file that contains the power and the path length for each ray emitted from the light source and detected by the receiver. By importing this output file into any computational software like MATLAB, we can compute the channel impulse response and all related channel parameters For example, the channel impulse response can be constructed by this formula, where N here represents the total number of received rays, Bi and tau I is the power and the propagation delay of the ice ray received by the detector. So integrating the channel impulse response can give me the DC channel gain, and here the bus source can be given when we're taking the logarithmic scale for the DC channel gain. Okay, and I would like to mention that during the simulations, we can normalize the transmit bar to unity, and normalizing the transmit bar to unity can allow us to further scale the received power to any given value of transmit power. Okay, so far so good, but this methodology is still a ray tracing simulation method. So it has to be validated or verified at least once against the measurements. And that is what we have done here by considering the frequency sweeping technique using a vector network analyzer with a two-port, where we connect the transmitter front end in one port and the receiver front end in the second port. And here we measure the difference, or we compare the signal we transmitted from port 1 and the one we received from port 2, so that we can characterize the VLC or Li-Fi channel. We done this experimental verification to different scenarios. For instance, for single input, single output scenario, we consider three cases. The first one, we have transmitter and receiver facing each other with a perfect alignment, so that we ensure that we have a perfect line of sight connection. In the second one, we make TX and the RX facing upward, so that the first order reflection can be received, but there is no line of sight. In the third scenario, we consider that TX and RX facing opposite to each other, so that we can see only high order reflections. Okay, for those scenarios, we did the experiment in this room and we obtained our results. And then we have modeled the typical room in Optic Studio platform, as you can see here on the right-hand side, and we run our ray tracing simulations and we obtain the results. Comparing them together, we can see here for the frequency amplitude response for the three scenarios and the channel impulse response as well. So the key message from here is that the results show a very strong agreement, which confirms the accuracy of the proposed modeling approach in the scenario. We also consider MIMO scenario, and we did the same by also investigating the amplitude and the phase response. And here I would like to mention the cooperations between our team at that time at Uzziya University in Istanbul, led by Professor Murat Hussein, and the Fraunhofer HHI team, led by Professor Volker Jankovic. And also, we have matched and verified the ray tracing approach with vehicle-to-vehicle scenario, where we cooperated with Port Hussein in Turkey and led by our colleague Bassam Ali and Dr. Ibra. And here we can see also a very good agreement between the ray tracing simulations and the measurement. So this phase was related to the experimental validation with the proposed ray tracing methodology. That is the reason, or that motivates us to utilize such a methodology in order to channel modeling and characterization for different vehicular scenarios, including vehicle to vehicle with both headlight and tail light, vehicle to infrastructure, and the infrastructure to vehicle with both street light and traffic light. And in the third phase, we investigated the possibility of designing the car and achieving the omnidirectional coverage. In fact, in this phase, we try to answer a question about the number of photodetectors required to ensure the coverage for all vehicular route types and scenarios. So let's start by phase 2 and by vehicle-to-vehicle scenario, where we consider either headlights or tail lights as a light source, and we have two cases. The first one is a perfect alignment, where the two vehicles follow each other with a perfect alignment. The source vehicle utilizes its headlights as light sources, and it has a commercial radiation pattern, comes from Philips fluorescent Clipper white LED, and the destination vehicle equipped with a photodetector installed as the center back of the vehicle. Later, we compare also the contribution of using two photodetectors instead of one in the middle. But here we have conducted the retracing, and we introduced a closed form bus loss model for this scenario. And the proposed closed form bus loss model here contains the effect of the distance, the extension coefficient of weather condition C, and we included D as a decaying factor that account for the asymmetrical radiation pattern of the high beam light source under consideration. As you can see from the simulation results here, that the proposed model provide a very good agreement with the retracing measurements. We also bring here a benchmark, which is the linear model presented earlier in this work, and this linear model can only match the results at shorter distance up to 25 meters. We utilized the proposed buses model and derived the maximum achievable distance that we can achieve while ensuring a target data rate and reliability. And here we see how much the distance can be achieved in different weather conditions. And as I mentioned earlier, we show here the advantage or maybe the additional distance that we can achieve if we consider the two photo detectors as the edges instead of the single photo detector in the center. And of course, here we normalize the power to be a fair comparison as well. We then consider the tail light as a light source, and here we started by measuring the radiation pattern of different commercial tail lights from different cars, including BMW, Audi car, and Nissan. And here as well, I wanted to acknowledge the cooperation with the team in Northumbria University, led by Professor Zabih Kasabloy. And here we consider the same vehicle-to-vehicle scenario and introduced a nice Barcelos model that can fit well with the retracing measurements for all vehicles or for all car tail lights under consideration. Same we did here. We consider this Barcelos model, and we consider the channel impulse response obtained from the retracing, and we investigated the RMS delay spread in different scenarios. And the key message here is that when neighbor vehicle increases, the RMS delay spread also increases. And this is due to the induced multibus component for neighbor vehicle and road reflectance. The Barcelos model is again utilized to derive the achievable distance at targeted bit rate and data rate, and we consider different bandwidths and all car models under consideration, and we show how much communication distance we can achieve, of course, for simple non-return to zero on-off-key modulations. And this work has been published in IEEE Photonic Technology letter in 2021. Then we have considered a more realistic scenario in which we know that in practice vehicles are not perfectly aligned. So therefore, we need to consider the lateral shift as well. But in this work, we consider the lateral shift, longitudinal distance, weather type, transmitter beam divergent angle, same as the receiver aperture side. And we derived a closed form expression that can match all simulation parameters. And here we show in this figure two benchmarks together with the ray tracing simulations and the proposed model. The first one is utilizing the Lambertian source together with the well-known Beer-Lambert formula that model the weather condition. And the second benchmark is a symmetrical source pattern together with the Beer-Lambert formula. And what we can see here is the Lambertian model failed to match the ray tracing simulation for all scenarios and distances, especially for larger distance. But the asymmetrical source pattern together with the ideal Beer-Lambert formula can match the results for clear weather conditions. For non-clear weather, however, only the proposed model can provide a very good agreement with the ray tracing measurements. Okay, we also verified the proposed model at different receiver aperture and at different lateral shift as well. The work has been also published in IEEE Transaction in Vehicular Technology in 2020. Then we have moved to the infrastructure to vehicle communications. And as I mentioned, we have here two cases. The case when utilizing the traffic light and the case when utilizing the street light as a light source. So for the first case here, we consider that the source or the transmitter here is the red traffic light. and we consider a commercial type from USRAM, where the vehicle is equipped with two photo detectors installed in the mirror of the vehicle, right? And then we consider three scenarios by changing the lateral shift between the vehicle and the traffic light. Here is the typical radiation pattern of the red traffic light. Based on this scenario, we have introduced the channel model, and we have also compared the proposed model with the retracing measurement test. And as you can see here, the nice thing that the proposed model provide very good match with simulation results in both linear and logarithmic scale, which is interesting as well. Okay, and then we move to this interesting scenario where the street lights can be used for as internet access points along the road so that the vehicle can receive the internet services while driving. And in this scenario, we can notice that, yeah, before moving forward, I wanted to highlight that we utilize a commercial street light pattern from Vestel, which is denoted as M4S, and the more details can be found in this reference. But here, what is different in this scenario? So when we see this scenario, we can see that the street light poles are uniformly distributed along the route and with a specific spacing distance. And this is according to the road regulations. Okay, that's great. So now, imagine the vehicle under the street light pole here. So, and it equipped with a receiver in its top. So the vehicle here at this point will receive the maximum power, right? And then this power will reduce gradually when the vehicle move away from the street light pole until reaching to the minimum value when the vehicle reaches to the center point between two street light poles. What's happening after that? When the vehicle continue moving, the received power will increase again. Why? Because the vehicle approach another street light pole, which we can see here along the road. So this happening along the road, repeated many times along the road, which can be translated to periodic behavior for the bus laws. We translated this and we introduced for the first time a sinusoidal channel modeling or a sinusoidal bus loss model for infrastructure to vehicle with a street light. Here is a model which has CB and CSA, where 2CB represents the peak-to-peak change in the received power, and CSA is the sinusoidal axis. So this model and those factors, the CB and the CSA, has been derived by finding two functions that contain the effect of all system parameters, including the lighting pole, HV, the height of the lighting pole, HV, the height of the vehicle, HV, the distance between two lighting pole, which we say it is PT, or the separation between the lighting pole, the lateral shift, DH, and the diameter of the photo detector, DR. So this model, we introduced its results for different ranges of simulation parameters or with system parameters according to the regulations, right? For instance, here we show in this figure how the proposed model perform for different receiver aversion. And here we show the impact of lateral shift in the proposed model. And in the next slide, we show results for the proposed model at different pole height and at different spacing distance between poles, same as for different lateral shift values. And the key message here, as it can appear here, that the proposed model can provide a very good agreement with the results for all HV, HVDT, and other simulation parameters. And we have here the maximum difference is 0.5 dp, which is very interesting. And the work has been published in IEEE transaction in VCRAP technology. Okay, now I will move to the second phase of my talk today, which is car design and achieving the omnidirectional coverage. And as I mentioned before, we would like to answer the question about the sufficient number of required photo detector to achieve the omnidirectional coverage. We need to ensure receiving the signals for all vehicular scenarios and route types under consideration. So if we look to this photo, this is all scenarios we have considered So, for example, you can notice vehicle-to-vehicle in the same lane, or vehicle-to-vehicle communication for in different lanes or in multi-lanes. Same as vehicle-to-vehicle in Y intersections or in T intersections. Also, vehicle-to-vehicle communicating with each other in the curvature rule. And also the vehicle should receive the signal from the traffic light and the street light. Here you can see all scenarios under considerations with more mathematical representations. I will not go much details to that, but of course you got the idea that we consider all possible scenarios along the road, including also the T and the Y intersection, same as the curved road as well. And this is for I to V scenarios using a traffic light and the street light as well. So for all these scenarios, we came up with that 9 photodetectors would be sufficient to avoid outage for all communication scenarios under considerations. Here, those are the 9 detectors that are installed, 2 of them at the back of the car, another 2 here at the back, but here at the left back, and one in the top of the car, 2 installed in the mirror of the car, another 2 in front of the car. So those 9 photodetectors, as I mentioned, this is our answer to the questions. And those can achieve this connectivity in 2 scenarios, the low speed communication scenario, which is sufficient for most safety applications around the 10 kilohertz, and for the high-speed communications with B equal 10 megahertz that can enable video streaming. Right? Here we show the received power at all communication scenarios under considerations, and also we see the effect of different factors, including, for example, in curvature rule, we show how the radius of the curvature rule can affect the signal and how the lateral shift as well. And in Y intersections, we show how the angle of Y intersection can affect the communication signal or the total received power. In the next slide here, we show the contribution of each of photodetectors from the 9 ones under consideration in each scenario. Here we just consider the last 3 scenarios just for the limited time. So for this is the infrastructure to vehicle with the street lights and a different lateral shift, just to show you how that each of the detector can contribute to the communication according to the location of the car along the road. Okay, and this work has been published in IEEE Access. Okay, till now, this is what I wanted to present according to the channel modeling that we have utilized in V2X communications. Next, I would like to highlight some challenges for Wi-Fi in V2X communications. Those challenges started with the line of sight dependency of Wi-Fi system. As you know that we require line of sight connection between the transmitter and the receiver in order to establish the connections. And another challenge is that V2X communication or V2X Wi-Fi communication is sensitive to weather and ambient light, right? And also here, I would like to mention a scenario that we didn't consider in this presentation, which is parallel vehicle-to-vehicle communications. So if we have 2 vehicles moving parallel to each other, we cannot utilize the headlight or tail light for communications. So here I would like to mention some innovative solution to address these issues. For example, multi-hub relaying techniques, which can solve the problem of blockage if we don't have line of sight, specifically if we talk about intermediate vehicles. So what we propose here is that the intermediate vehicle can receive the signal from the vehicle in behind, decode it, and retransmit again to the in front vehicle until reaching to the destination. Of course, this will require additional efforts to develop MAC layer protocols and the network protocols that can manage this kind of communications. Another innovative idea that I would like to highlight here is the utilization of reconfigurable intelligent services in V2X Wi-Fi communication. As you know that in parallel communication, as I mentioned, headlights or tail lights cannot be used to enable communication between these 2 vehicles who is parallel moving together. So what we are saying here is installing reconfigurable intelligent services along the road installed in the street light poles can allow the signal move or the signal that can transfer from the source and then reflected by the RIS to reach it with a destination. Here is a mathematical representation for our vision here. And actually, such idea we have presented or disseminated in IEEE communication letter recently. Okay, the same the same technology, reconfigurable intelligence services, can be applied for infrastructure to vehicle with a straight line in order to improve the communication performance and also in order to solve the problem of blockage if we have, let's say, trucks that can block the signal as well. And we have also introduced the idea and we provided some initial results in IEEE transaction integrated technology in 2025. At the moment, I would like to conclude my talk, and here I wanted to just give you a takeaway that the Wi-Fi is a promising technology for V2X communication. In my opinion, Wi-Fi or visible line communication is a natural wireless connectivity solution for V2X networks. And now, since we have already established some realistic channel buses model for V2X Wi-Fi communications, also, we see that investigating the system development over network performance, including handover McLayer protocols, throughput packet delivery ratio, become accessible now. We would like to mention that the demand for high data rate in V2X application is continuously increasing, right? Which make it is important to integrate Wi-Fi with other emerging V2X solutions, especially CV2X and the millimeter wave, because both of them can achieve high data rate in different scenarios, right? And that is also will require some development of dedicated channel models and the efficient switching algorithm. So in addition to the configurable intelligent services and the multiple relaying techniques, I would like to acknowledge the roles that artificial intelligence can play in such scenarios, specifically for optimization and the switching techniques for V2X communications. So till the moment, I have finished my slides and I would be happy to take any question you may have.
Thank you very much, Dr. Hussein, for the insightful presentation. And I do see two attendees, so I would like to open the floor. I'm wondering if whether Aisha, Maghrawi, or Khulud may have some question. I don't know if they do hear us. Maybe not. Anyway, if you do hear us, please, you have the opportunity to ask questions to Dr. Eldeeb. Meanwhile, I will have quite a few questions here.
Sure. Yeah.
Yeah. So first of all, I would like to ask you actually about, you were talking about Li-Fi around slides, I think 9 and 10. And of course, Li-Fi do offer several advantages, such as high speed, security, large bandwidth. So with these advantages, how do you see the most impactful actually for the V2X applications?
Sorry, the most what?
Pardon me?
The most, the
Yeah,
most
the most-
benefit you mean?
The most impactful among those advantages for V2X applications.
Yeah, that's really interesting questions. You know that all of these advantages can contribute to the designing and actually having efficient communication system. But if I am going, if I would choose, so the first impactful insight here is the bandwidth. So the ability to achieve high data rate in V2X communication can enable or that can open the door for many interesting applications, including video transmission, entertainment along the road. But another one as well, which I am really like it, which is enabling illumination together with data communications. This is for V2X and also in indoor applications. You know that energy is one of the critical parameters, not only in communication, but in the world in general. So having a communication system that can also provide energy efficiency. This is one of the important advantage. This is my opinion. Yeah.
Yeah, indeed. Yeah, thank you for your input. I see we have one more attendee so far, so I'm wondering if you would like to address any question. Yes, I see on the chat. So
Okay.
let me check the message we get from from Aisha, and she's actually thanking you, Dr. Hussein, for this brilliant
Thank
talk.
you.
And if she
Thank you.
has any questions, she can do it by chat
Sure.
if she likes. Of course, this is the same for the other attendees. So we appreciate if you have any questions, just like you can leave them on the chat, and we appreciate the insight from Dr. Eldeeb. My next question is going to be about the deployment challenges. You talked about the deployment challenges, and what do you consider actually the main barrier to real world deployment in vehicular environment from your perspective?
Okay, that's also amazing questions. See, to be honest, till the moment, still the real deployment for V2X based on Wi-Fi communication is still in the early stage. But some barrier here would be actually can be the integration of the communication platform to the existing infrastructure. Of course, some of the automaker companies started to do this, but still not in the wide adoption as we saw, for example, in radio frequency. So this is one barrier. Another one also is that Wi-Fi communications. I am not with those that see it as like it should replace radio frequency. No, I am seeing it a complementary technology to radio frequency. So both of them should be integrated together. So here I am looking for hybrid communication, hybrid integration between Wi-Fi and RF. With this way, it would become easier for us to see real or to see commercial platforms for Wi-Fi based V2X communication. But relying only on Wi-Fi from the business point of view, it might be not the good options, but integrating both of them together would be more robust. Specifically, that we saw during the presentation that RF and Wi-Fi has different advantages. For example, Wi-Fi can perform well in short-range communications and in high-traffic scenario, but RF can perform better if we would like to have a long-range communications. So if you convince any business or any company to just utilize in their car Wi-Fi communication, of course, they will not agree because it will not perform well if we talk about kilometer communications. But if we have this integration, I think that can make it easier for automaker companies and even for any industrial partners to go forward with this technology.
Yeah, indeed, Dr. Eldeeb.
Thank you.
How do you see this integration actually between RF and Li-Fi technologies? How do you see this integration
Yeah.
effort going on? Do you see that it's
Uh,
something we can think about like in the
yeah.
near future or yes?
Yeah. Actually, this is also nice. I see extensive research efforts nowadays that can provide integrated system between RF and different optical wireless communication technologies, but still the simulation or theoretical based scenarios, in my view, still require practical demonstration of such integration between RF and Wi-Fi. But I think it will come soon because you know that we cannot rely only on one technology. As I mentioned before, one of them can perform well in some scenario, but it will fail in another one. So the only possible way is to benefit from each technology and in order to, ensure the targeted data rate and reliability in all scenarios in our life, especially in V2X communication, where we face several challenges, including the blockage, weather conditions, and also mobility. So I think it is going on, but still at the moment, we are still in the stage of theoretical and simulation stage.
Yeah, thank you very much. And my last question, actually, it goes along your quite last slide where you were talking about the future innovation and the emergent techniques like AI or
Mhm.
RAS. So my question there, and your talk is part of the Young Professional VTS Young Professional webinar series. So,
Mhm.
what skills or areas the young professional focus? You may advise them which areas young professional can focus on to contribute in this
Mhm.
field.
Yeah, thank you for those questions. Uh, in my view, and I think you will agree with me, that skills related to artificial intelligence nowadays is very important, and it will highly contribute to advancing not only Li-Fi V2X communications, but other communication systems as well. But in Li-Fi communication specifically, still some characteristics and some maybe some conclusion we didn't reach about. I believe that with the skills in artificial intelligence, utilizing machine learning, deep learning, that can help us to further, conclude and highlight the contribution of those characteristics as well. So having skills in artificial intelligence together with wireless communication fundamentals or the basics of wireless communications and a little bit for optical wireless communication specifically would be very important nowadays in order to further contribute to the technology and advance it. Also, uh, I advise young professionals to investigate the hybridization between this technology with other technology as well. I saw some earlier work in integrating millimeter wave with visible light communications. But the work is still in a channel modeling stage. And as I mentioned, still further skills related to network layer is required in order to complete the work. And one more area and one more skills I advise students and even younger professionals to explore is the security. You know that it is not only important to have the communication services, but also we need to ensure that it's secure. So the security should be also in the top of the V2X Wi-Fi communication network as well. So this is my advice, and I hope it will be useful for the young professional attending with us. Yeah.
Yeah, indeed. I believe it's gonna be useful to them.
Yeah.
Thank you very much. We come actually to conclude our webinar today. I would like to thank you one more time for your insightful presentation on Li-Fi enabled V2X realistic channel modeling and innovations for next generation connectivity. Your work represents an important actually step forward, enabling more secure, reliable, and resilient actually intelligent transportation systems. The record, as you may recall, of this webinar will be available soon on our VTS YouTube channel. Thank you very much one more time, Dr. Eldeeb, for your availability, and we wish you all the best for your future endeavors. Thank you very much
Thank
for
you.
you and for
Thank you very
our
much.
entities. Thank you very much.
Thank you. Thank
It
you
was a
very much,
pleasure
Chedlia, once again.
having you
Yeah, my
today. Thank
pleasure
you.
as well. My
Thank you
pleasure.
very
Thank
much.
you very much.
Thank you.
Goodbye.
Bye bye. Thank you.